Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 11th, 2025. We're looking at an ICLR conference paper, One-Step Diffusion via Shortcut Models, published on January 22nd this year, so just a little over 3 months ago. This paper tackles the slowness of some AI models, like diffusion and flow matching models, which generate data by many small steps. This paper introduces shortcut models. The core idea is simple. These models learn to take bigger shortcut jumps in the data generation process. They do this by being told not just the current state, like noise level, but also how big a jump they should try to make. Alright, so this first figure really highlights the practical benefit. We're looking at images generated by traditional flow matching models on one side. Remember, these typically need many small steps, and these new shortcut models on the other. The comparison is across various inference budgets. That's essentially the number of computational steps the model is allowed for generation. At many steps, like 128, both methods produce clear images. But when restricted to just one step, the traditional model's output becomes very indistinct, whereas the shortcut model still generates surprisingly sharp results. This visual really underscores their speed advantage. Let's move on to the next part regarding one-step diffusion via short-queue. Alright, so building on that speed advantage, this next figure gives us a conceptual overview of how these shortcut models are trained. On the top, in part A, you see the standard diffusion or flow matching process, many small, careful steps. But in part B, for shortcut models, the training encourages the model to learn how to make larger jumps. It does this using a clever idea called a self-consistency loss. This essentially teaches the model that making one big step should yield a similar outcome to making two sequential, smaller steps that cover the same ground. This joint training approach is key to their efficiency. Okay, so this table then lays out the precise steps. Algorithm 1 for training shortcut models, and Algorithm 2 for generating data with them. Algorithm 1 details how the neural network, _S_theta, learns from flow matching targets for direct steps, and through that self-consistency idea, where one large step, say of size 2D, should match two smaller sequential steps. This often guides the model along paths defined by an ordinary differential equation, or ODE, which mathematically describes continuous change. Then, Algorithm 2 shows sampling. Starting from noise, it iteratively applies the model using noise level T and step size D. Error generating script for segment 6. Moving to the results, this table compares different generative models on the Imaginet 256 dataset. We see metrics like FID. That's fresh inception distance, a common score where lower means more realistic images. It also lists sampling steps, parameter count, which tells us about the model size, and epochs trained, meaning how many times the model saw the entire training dataset. Notice the shortcut model XL achieves a fresh inception distance of 10.6 with just one sampling step, showing excellent quality even at high speed, and it remains competitive with many steps too. So, as we've seen from those results, these shortcut models really tackle the speed issue inherent in many generative approaches. The key takeaway here is their ability to produce high-quality results, even with very few, or just a single computational step. They achieve this by learning to take these larger shortcut jumps, guided by that self-consistency idea during a single, streamlined training process. It's a neat way to get speed without sacrificing too much quality or adding a lot of complexity. That's all for this AI Research Roundup. Thanks for tuning in.